Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about this subject of harmonic analysis, which gives you extra motivation for looking at the notion of Lie groups that we've been looking at in this playlist. And what I want to do is I want to revisit the notion of Fourier series that you should have seen before and show how symmetry explains why this is a really important notion. And when you look at this more general version of Fourier theory from the perspective of symmetry using Lie groups, you get what's known as harmonic analysis. Okay, so let's start by reminding ourselves, what does Fourier series are, okay? So here we want to look at a function f of a complex variable x, and we can expand a periodic function like this with period 2 pi in a form like this here. So it's a sum from n equals minus infinity to infinity of Cn e to the I n x, where so the n's here range over the integers, and these Cn are complex coefficients. Okay, so that's something that you should have seen before. And what's the Lie group that applies in this case? Okay, so the Lie group that applies in this case is basically the following one here. It's the circle group. Okay, so why is the circle group, and how do I want to think about the circle group? One way to think about the circle group is as a quotient group of R modulo lattice inside here, so I'll make it 2 pi z. Okay, so we've seen this construction of a quotient of a Lie group before, and this will give you a Lie group R mod 2 pi z. And this Lie group, of course, is isomorphic to the usual circle group. Okay, and so since you're going modulo 2 pi z, that's why you can consider functions which are periodic with period 2 pi as just functions on this Lie group here. Okay, so that tells you that this e to the I n x, for example, which is 2 pi periodic, you can think of as inside this Hilbert space L2S1, okay, of square integrable functions on S1. Okay, so I want to rewrite this theory of Fourier series and put it into a more sort of abstract language. So one way you can write it is that you have a Hilbert space decomposition of this L2S1. So you kind of want to think of this as just square integrable functions which are periodic. Okay. And then since everything has a form like this, you can express every element in here as a sum like this. So you can form the Hilbert direct sum of the vector spaces, which are basically this coefficient times that, so just C times this. So these one-dimensional vector spaces, C times e to the I n x. Okay. So you have to take the Hilbert space direct sum, of course, because you don't just look at finite linear combinations of these functions here. You have to look at infinite linear combinations which satisfy the required convergence property. Okay, so that's a statement basically of Fourier theory. Okay, or the most an important part of it. And so the question is, well, why is this such a useful decomposition? And the answer I want to give to you in this video is very simply symmetry. Okay, so symmetry is the answer to this question, and the symmetry that's involved here is the symmetry of a Lie group, and it's going to be this Lie group here, the circle group, which we can think of as R mod 2 pi z. Okay, so let's see how to set that up. Okay, so this is the harmonic analysis setup. So we have the Lie group S1, and being a group, it can act on itself. It acts regularly on itself. So let's just remind ourselves what that means. So if given any t inside S1, you can act by this t on S1. So you have an action of t, alpha t, on S1. So that's mapped from S1 to S1. And what does it do? Well, if we use this viewpoint for what S1 is, so this is a group with an addition on here, it just translates by t. So you just add by t. So in other words, it sends x to x plus t. X gets sent to x plus t. So that's the alpha t, the action of t on any point on that circle, any point inside here. Okay, so that's an action, but we're not looking at S1 here, we're looking at L2 of S1. And the point is that since we act on S1, we also act on L2 of S1. Let's remind ourselves how that works. In this case, the group is abelian, so we can simplify the definition here. Okay, but the point is, yes, now L to S1 is also an S1 module. So how does that work? So if you're given a function here from that's in L to S1, so that's a function from S1 to complex numbers. Okay, we get a new function t dot f. What we do is we go apply alpha t first, and then we evaluate via f. So you do alpha t first, and then you evaluate by f. Okay, so just to make it absolutely clear what this means, okay, what is this function t dot f? When you evaluated x, you firstly apply the action of the group element, t, and then you apply f. Okay, and being an abelian group, this is fine. Okay, and now I want to present this result, this Fourier series result, in a more sophisticated form. Okay, it looks like the same. It's the same formula. Okay, L to S1 is the Hilbert space direct sum of these one-dimensional vector spaces, and these one-dimensional vector spaces just C e to the I n x. But this is not just a Hilbert space equality here. This is also has S1 modules. Okay, that's what I want to claim. So the extra piece of information that I have now is that now this decomposition is a really nice decomposition. So why is this such a useful decomposition? Okay, so why do we, in other words, why do we pick this basis? Okay, this basis for the Hilbert space, why do we pick that one? It's because it's going to give us a decomposition not just of Hilbert spaces, but of S1 modules. Okay, and what that basically means is that each of these one-dimensional vector spaces is actually stable under the action of the group. Okay, it's stable under the action of the group. In other words, any one of these basis elements, f of x equals e to the I n x, is actually going to be an eigenvector for the S1 action. Okay, so let's see why that's true. Okay, we want to show it's an eigenvector for the S1 action. So let's check and make sure it is. Okay, so here's our function f of x, e to the I n x, and we want to apply t to it and see that we get a scalar multiple of that one. Okay, here t is fixed. So what is the action? Firstly, we act by the group element t, so that sends it to x plus t. And then you evaluate the function at it, which is e to the I n. E to the I n at this new value here. And then what you can do is you can just expand that out. It's e to the I n t times e to the I n x. Okay? And this e to the I n x is the original function f of x. So what we see is that when we let this element t of the group S1 act on this exponential function here, all it does is it scales it by this complex scalar e to the I n t. Of course, when we vary the t, this scalar will vary, but still, for each and every t, this just scales it. Okay, so you remain inside this one-dimensional vector space. So this one-dimensional vector space is closed under the action of S1, and this is actually a decomposition of S1 modules. And that's the reason why this is such an interesting decomposition. Okay, so there's quite a bit there, but I want to give you this little scholium to sum up some extra interesting features of what goes on, because it's quite a wonderful theory that's associated with this. So firstly, let's look at this eigenvalue. Remember, it varies with each element of the group. So it's really a function from the group to the complex numbers. Okay, so each element of the group spits out an eigenvalue, and that eigenvalue is e to the I n t. So it's a function from S1 to C that maps t to e to the I n t. And this type of function is actually quite a nice function because it's actually a group homomorphism from S1 to actually, you can even say it lands inside the non-zero complex numbers. This exponential is always non-zero. And the point is that, well, sums here get sent to products over here. Okay, so that's the basic property of the exponential function. So this is actually a group homomorphism from this abelian group to this abelian group here. Okay, so these are group homomorphisms, and it's continuous. It's the exponential function. Okay, so it's a continuous group homomorphism, and continuous group homomorphisms are called characters. Okay, so these eigenvalue functions, right? Like eigenvalues. Okay, they're now considered functions on the group, and they're called characters. And they're actually continuous group homomorphisms. So what you can do, and this is part of the general theory, is you can look at the set of all such characters. And what we have here is we denote it with the S1 with a check. That's the dual symbol. It's called the dual group. So these characters themselves are a group. So how are they a group? Well, basically you're mapping from a set to an abelian group, so you can do pointwise multiplication over here. Okay, so for example, if you have a chi-n, for each integer you have a chi-n. If you do chi-n times chi-m, chi-n times chi-m, okay, you basically multiply e to the int by e to the imt, so that's e to the I n plus nt. Okay, and that gives you a different character, one associated to n plus n. So what we find out is actually, and it's quite easy to see from the setup here already, is that the dual group of this S1, it's quite easy to show that the only characters are of this form. So the dual group is going to be, well, it's parameterized certainly by the integers. And I've also shown you how the group operation works in this dual group, okay? If you put chi-n and chi-m together, you'll get chi n plus n. So it's the same as the addition on the integers. So what we'll find is that this dual group, okay, is actually just a group of integers, and this also gives you the decomposition. Okay, it tells you what sums are there are here. So the grading of this decomposition, okay, so how many components are there for that? There's one for each element of this dual group. Okay, so let's see why this S1 decomposition that we saw that corresponds to Fourier series is so important. Okay, so what we'll do is we're going to consider a linear map from L to S1 to L to S1. We'll call it T, which is in some sense S1 symmetric. Okay, so this is the key point where the symmetry sort of comes in. Okay, so what does that mean for it to be S1 symmetric? That means that it commutes with the action of the group. So if you want to act with a group element T, T dot F, and then apply this big T there, that's the same as if you applied the T first to get you an element of L to S1 over here, and then act on it with the group element. And this is for every group element. So this is for all T inside S1. Okay, suppose that you're in that situation here. Okay, so there's plenty of instances where you might see this sort of thing. For example, if you look at differentiation, okay, you can translate and then differentiate, or you can differentiate first and then translate. Okay, so that's an example. So what happens then? In this case, what we will see, in fact, is that if we apply this linear operator, which is S1 symmetric, to this component of the decomposition, C e to the I n x, it is actually stable under T. So this will be contained inside C e to the I n x. Okay. And another way to say why, well, this is a very interesting result, and another way to see why it's really interesting result is, of course, what does T do to this e to the I n x? Okay, it lands inside here, so it's just a scalar multiple of e to the I n x. So in other words, this e to the I n x is an eigenbasis, Hilbert space eigenbasis for T. Okay, so this is something that you get. This is an eigenbasis very often. How often? Whenever you have this T, it's just S1 symmetric. As soon as we have this symmetry property of this T, okay, then we get a nice eigenbasis for it. Okay, and that explains why it's so useful. Okay, so let's see why it's true, and actually it's quite easy to do that. We've more or less seen what we need to do. So what we're going to do is we're going to look at T of this e to the I n x here, okay, And what I want to show is that this itself is actually an eigenvector for the group action. Okay, so that's the thing that we want to show. So let's see why that's the case. Okay, so remember, this T is S1 symmetric, so these two actions commute. Okay, the T and the group action commute. So we can write this as T of T dot e to the I n x. And remember what T dot e to the I n x is. Remember, this is an eigenvector for this group action. So this, and the eigenvalue is e to the I n t. So this is T e to the I n t, e to the I n x. Okay, so x is going to be the variable on this S1. Okay, and this we think of as a constant, so we can pull it out. So this is equal to e to the I n t times t e to the I n x. So this t here, acting as t e to the I n x, what does it do? It just scales by this e to the I n t. This scales. So for each t, it scales by this e to the I n t. Okay, so that tells you straight away that this is also an eigenvector. And what's its eigenvalue? Eigenvalue is this e to the I n t. So it's chi n of t equals e to the I n t. But remember, we have this S1 decomposition of L2 S1. And it tells you that what are the eigenvectors with this eigenvalue? Okay, it's basically e to the I n x. Okay, and the scalar multiples of that. So this eigenvector has to be some scalar multiple of e to the I n x. So it's inside here. And that finishes the proof of this fact. It's quite simple like that. Okay, so let me just reiterate here and explain again why this is such an interesting thing, okay? The only thing, so firstly, it's going to tell us a little bit about linear maps from L2 S1 to L2 S1. And it's important here to note that this S1 is a group in this case, so it has some S1 symmetry, okay? So what it does is it basically gives you an eigenbasis. And it gives you an eigenbasis as soon as you know that T is S1 symmetric. That's the only piece of information that you know about that. And immediately it tells you, well, the basis that you get, that you use in Fourier series, that's the one that's going to be useful. Okay, that's the one that gives you the eigenbasis. Okay, well that's great, and that's looking at the Lie group S1. So what about other Lie groups? Okay, are they also useful? Well, let me show you another case where it's useful. The theory gets a little more complicated, so I won't go through all the details, but at least let me hint for you the basic idea of what happens. And this is usually the next step up. Okay, you have to go up in dimension, and here we're going to look at what are called spherical harmonics. Okay, so here we're going to look at functions on R3, and I want to look at a particular linear map from L2 R3 to L2 R3. Okay, this one here is basically, so suppose the coordinates on R3 are x, y, and z. Okay, as usual, we can also pass to cylindrical, spherical coordinates. So we have a radius, which is the square root of x squared plus y squared plus z squared. And consider this operator here. So given a function of x, y, and z, we look at its Laplacian, so d2 dx squared plus d2 dy squared plus d2 dz squared. Okay, and then we add to that f of r times that function. Okay, so to a function, we take this Laplacian of it, and we add to it f of r times that. And of course, from the nature of what this has spherical symmetry. It has, you can rotate, okay, in R3, and it has this spherical symmetry about it. So it has SO3 symmetry. And this SO3 is another Lie group. Okay, so here we said we have this T has this S1 symmetry, then we can immediately get some eigenbasis for it by looking at the action of the group and decomposing it with respect to that group action. So we're going to do a similar thing here. Okay, we're going to now say, oh, instead of trying to look at the eigenbasis for this directly, we look at the eigenbasis or something that's like an eigenbasis for the SO3 action. Okay, so this idea, what I've shown over here, suggests what we should look at is L2 R3. SO3, of course, acts on R3 because this is a subgroup of the general linear group on R3. So it also acts on L2 R3 in a similar way that S1 acts on L2 S1. Okay, so that's something that we have. Actually, I want to reduce the space a little bit, and the way I'll do it is as follows. Okay, what's an easy way to get a function on R3? Well, if you study, for example, oh, by the way, I should mention that this particular linear operator occurs in the Schrödinger equation, which is something that's very important in physics. And that's one of the main uses for this theory of spherical harmonics. Okay, and so you use this linear operator because basically this is the differential operator that gives you the differential equation, which is Schrödinger's equation. Okay, if you choose things correctly. So that's a differential operator that's used in that differential equation. Okay, and one of the tricks that you have when you play around with differential equations is you use separation of variables. So we're going to do a similar sort of thing here. We're going to separate out using spherical coordinates the radius part and the one that uses the spherical coordinates theta and phi. Okay, so the way I'll set it up here, I'll just do the simplest version of that. I'm just going to pick some function of the radius, big R of little r, okay? And of course, if you have some function like that, that also extends to a function of all of R3, okay? It doesn't vary when you change the spherical coordinates, theta and phi. Okay, so it's SO3 invariant, okay? So you can always have a product. You can look at products of functions of the form R of R and S of theta phi. Okay, so we fix this R of R now, and we're going to look at all these functions of theta and phi, and we'll think of this S as a function in L2 S2. S2 here is the two-dimensional sphere. Okay, so of course, since how does SO3 act on this? Well, it's going to leave this fixed, so it really just acts on this S of theta phi. Okay, it's just moving the theta and phi around. You're just rotating that sphere around. Okay, so they're all isomorphic SO3 modules. So the main thing to look at is the this L2S2 as an SO3 module. Okay, so what we saw before is when we looked at Fourier series, okay, we wanted to decompose L2 of S1 as an S1 module. So what I want to show you here is I'm going to show you, well, how can we decompose this L2S2 as an SO3 module? Okay, so SO3 acts on S2. Okay, the unit sphere is going to be stable under rotations, so it also acts on L2 of S2. And in that way, you can extend it to the action of functions like this, and so also more generally functions on R3. And I'll just state for you the main theorem so that you can see how it's rather pretty, that you can actually analyze this, but it's more complicated. Okay, so what is L2S2? It is an SO3 module, but when you decompose it and it's an SO3 module, okay, you can't write it as a direct sum of one-dimensional modules. Okay. In fact, what you have here is you have a direct sum of SO3 modules, often denoted VL, and there's one L for every non-negative integer. And this VL is actually going to be irreducible of dimension 2L plus 1. Okay. And you can write out quite specifically what these are. Okay. So they're known things. You can write down exactly what, give precise bases for these functions. And you can write them in terms of theta and phi, these spherical coordinates, if you like. Okay. I haven't written them here because they're quite complicated, the actual formulae for them, and not so useful. But the fact is that this exists, and this is a unique type of decomposition. Okay. And then once you have this decomposition, of course, you can let T also restrict that to the sphere and let it act on here. And then all of these VLs are T-stable as well. And that's exactly the type of thing that we saw before, okay? So if you have a component of the S1 decomposition of L2 S1, like this one here, you let T act on it, it's stable. Well, each of these components here are also T-stable, and that means that if you want to pick a good basis for studying this T, what do? You pick bases for each of these VLs, and that's the best way to study that linear operator. Okay, so to sum up, okay, if you happen to know that a certain linear operator like this, okay, has a certain symmetry, okay, then what you should do is you should study how that symmetry or that group, the corresponding Lie group, acts on that space, and that will tell you the most intelligent decomposition. I hope you enjoyed this adventure in pure mathematics.